Hi everyone, I am the founder of the Grey Blind Owl. Today we will continue with dynamic memory allocation with matrices. If you have truly understood the lesson we taught last week, believe me, you will not have any difficulty as we will not do anything different in this lesson. There will be two differences for the dynamic memory allocation we will do this week. The first one is the dynamic memory allocation adaptation due to the two-dimensionality of the matrices. The second one is the function prototypes and methods because of matrices. First of all, we will show dynamic memory allocation without using functions. Then we will talk about how to do it through functions. We include our libraries. We will also use stdlib.h for the dynamic memory allocation ready-to-use functions. Hashtag include stdio.h and hashtag include stdlib.h. We create our prototypes, float, pointer, open space for matrix, integer, and semicolon, and void free only in one line, float, pointer, and integer, and semicolon. I will mention these prototypes later. We create our main function. Here, integer main, the brackets and the curly brackets. Now we will create some integer variables, I and j for counter, row for the row number of matrix, and column for the column number of matrix. So integer I, j, row, column, and semicolon. As you know, if we want to make dynamic memory allocation, we must first define our array or matrices as an address holder. Okay, as an address holder. We define it as an address holder. Now, this time we want to use a matrix. So we have a two-dimensional array and we have to use 2 times reference sign for it. The first matrix for the part without functions, so matrix with function passive, and the second matrix with function active for the part with functions. Okay. Float, pointer, matrix with function passive, and the pointer matrix with function active, and semicolon. Now, at this part of the program, we need to knowledge about row and column. So the knowledge about the dimensions actually. We ask the user for the dimensions and we get them here. Printf, please enter the row and column numbers. Scanf, the person sign D and the person sign D. The first person sign D represents the row number and the second person sign D represents the column number, and semicolon. Here, execute, compile and run. As you can see, please enter the row and column numbers. I will enter here 4 for the row number and 5 for the column number. Okay, we are here. With this information, we can do dynamic memory allocation. Now, we have 2 dimensions, so we have to do dynamic memory allocation separately for each dimension, okay? We have to do dynamic memory allocation separately for each dimension. Firstly, we do this for the row number. This operation is called flagging by some groups. Okay, this is not common, but this usage is okay, flagging. We put a flag for each row, and after we will put columns like an array on these lines that start from these flags. Okay. We put a flag for each row, and after we will put columns like an array on these lines that start from these flags. Okay. Matrix with function passive is equal to float pointer because our matrix with function passive type is an pointer. Okay, this is an address holder and this is a two-dimensional array, so we have to use 2 times reference sign. Okay. And float pointer calloc row times actually not times row and a comma size of float and float pointer, because we put a flag and a flag has one dimension, so we have to use one reference sign. Okay, we have to use one reference sign and semicolon. Now we use a for loop for the columns. Now for I is equal to 0, I is less than row, and I plus plus, we are on the second dimension. Okay, we are on the second dimension, so we put the columns for each row. Okay, we put the columns for each row. So our for loop is related to row number, and matrix with function passive I, our index for our flex, our rows separately, and this is equal to float pointer, as you can see, every flag, column size of float for our elements. So our elements types float, so we put float type here, and we put these float elements into our flex for each row. Okay, we have successfully allocated space for our matrix. Now we can use our matrix, which we defined as an address holder, as a normal matrix from now on. Okay, we can use our matrix, which we defined as an address holder, as a normal matrix. In order to prove that our matrix is formed, we fill it with random values and print it on the screen like that. These parts are not important. I fill this matrix with random values, and I print these random values on the screen here. As you can see, for I is equal to 0, I is less than row, and I plus plus. For j is equal to 0, j is less than column, and j plus plus. Matrix with function passive I and j is equal to I plus float j over 10. This is random values. This is a random value and a semicolon. Okay, and after that we will print our matrix. For I is equal to 0, I is less than row, and I plus plus, and blah blah blah. Printf the person sign d dot 3f for the 3 digits after the decimal point, and matrix with function passive I and j and semicolon. Printf slash n and semicolon for the new row. Okay, here like that. 0, the first element, 0.1, 0.2, 0.3, 0.4. As you can see, 5 elements each row, and as you can see, 1, 1.1, 1.2, 1.3, 1.4, 2, 2.1, 2.2, 2.3, 2.4, like that. This is our matrix. As you can see, we have successfully allocated space for our matrix, and we fill it we filled it like that, and we print it on the screen. Now our work with matrix has finished, and we have to make it free. We have to make the columns free firstly, because we open space for them lastly. Okay, because we open space for them lastly. Here, as you can see, we allocate space for the row firstly, and after that we allocate space for the column secondly. So we have to make the columns free firstly. Because of this reason, we opened space for them lastly. After that, we can free the rows flex like that. For I is equal to 0, I is less than row, and I plus plus, free matrix with function passive I. Okay, that's it. And semicolon. And after that, we can free the rows flex like that, free matrix with function passive and semicolon. Okay. Now, in this part of lecture, we will do the same operations that we did above with the functions. Now, printf new part /n and semicolon. Now, firstly, we open space for our second matrix with the open space for matrix function, our new function. Matrix with function active is equal to open space for matrix row and column. Row and column. We need this information only. Row and column. Their dimensions. Like in the arrays. Okay. Go to the open space function here. Float reference open space for matrix integer row integer column. We create an integer variable to make it a counter integer I because we use only the row number for flagging. So we do not need an extra counter like J counter because we do not use an extra for loop with J counter. So we create a temporary address holder for our matrix here, float reference matrix. This is temporary. And we allocate a convenient space for our matrix and we put the empty set of addresses inside our temporary address holder. Matrix is equal to float pointer calloc row size of float pointer and semicolon. For I is equal to 0, I is less than row, and I plus plus matrix I is equal to this one, and we did this before here. But we do this time in the function open space for matrix. Okay, there is only one difference, and we returns the space to our main function. That is why we use float pointer for our function type, return matrix and semicolon. Okay, now we are here. We have successfully allocated space for our matrix. And again, now we can use our matrix, which we defined as an address holder, as a normal matrix from now on. And in order to prove that our matrix is formed, we fill it with random values and print it on the screen with the same operations. So I do not talk about these operations. And also you can make these operations between 75 and 8, 9 here with some extra functions. I do not want to take your time with this type of out of subject operations. Now our work with matrix has finished and we have to make it free, but we do that with a function for multiple use this time. Okay, and free only in one line, matrix with function active, our matrix, and we send our matrix to make it free and its row number. Go to the free only in one line, float pointer matrix and integer row, and we create an integer variable to make it a counter integer I, and we have to make the columns free firstly because we open space for them lastly. After that we can free the rows flex. For I is equal to 0 and I is less than row and I plus plus, free matrix I and semicolon. After that, free matrix and semicolon. This is for our flex. So this is our rows, and this is for our columns. And we only need the row number because we did flagging here. Okay. and we finish our program here, return 0. As you can see, new part, the same part actually, 0, 0, 0 0.1, 0 0.1, and the random and 2.3, 2.3. As you can see, they are the same matrices, and we did this part with no function, and we did this part with functions. Okay, we finish our program, return 0. That is it for this week. We have completed the dynamic memory allocation topic with this lesson. With this achievement, you will be able to create efficient programs where memory is well managed. You can find the code we used in the lesson in the description section. With the increase in the complexity of the codes, we focus less on some classical functions. So if you wish, you can improve your skills by upgrading these codes in a more appropriate way. We will continue next week with a very relaxing topic, scopes. So we will have more detailed information about the flow of our codes. Thanks for all your effort and patience. See you following lecture. Stay tuned.